We want to look at the property, the expectation of the sum of random variables equals the sum of the individual expectations. So the expectation of the sum equals the sum of the expectations. Just a little background. You probably already know this, but just to make sure we're all on the same page, an expectation of a random variable is just it's the mean, which is the same thing as the average, which is the same thing as a weighted average. So you have some random variable, capital X, and it will have a support of some set of, it could be discrete or continuous, I'm just doing discrete here, of a bunch of X values that the capital X could take on. So the random variable is capital X, and in lowercase are usually used as the values that this variable could take on, and the expected value would just basically be the mean of all of these. But an average is the same thing as a weighted average. If you think about, if you took the average of the three numbers 2, 3, and 7, well, you would add them up, divide by 3, the number of numbers, and you would get 4. But another way to look at it is it's the sum of each occurrence and the probability multiplied by that occurrence of the probability of that occurrence happening. And so you could look at this as probability of, so if you had 2, 3, and 7 in a hat, and you were just reaching in, randomly selecting them, there would be a 1/3 chance of you picking the 2 or the 3 or the 7. So all the probabilities are the same in this case, but they don't have to be. And so you could think of this as the probability of getting 2 times 2 plus probability of picking 3 times the occurrence 3 plus the probability of getting 7 times 7. That's basically how you do any average, which like I said, is just a weighted average. The probabilities wouldn't have to be 1/3. There might be a couple of 2s, so it has a higher probability of getting picked, but you'd still figure out the average in the same way. Okay, so just a little bit in the way of the way we're going to do this. It's pretty common to use summation, the capital sigma for summation, and basically if we express this like that and in a general sense, well, what we would do is we would take if we were only doing X, not X and Y, but just the expected value of X, then it's pretty common to put Xi and then so we start with I at 1 and go up to whatever, M or N or whatever you want to call the highest number. And then you would sum up all the occurrences of Xi times the probability of getting that particular Xi. And then if you had 2 random variables, well, there's 2 sets of this. And so basically you have to use a double sigma, and we could write it like that. So the occurrence of a particular X and Y times the probability of getting that particular XY. Actually, I need to use a different, I don't want to use I. We need to use a different letter for Y. And then you could, it wouldn't matter the order, but you could put, I'll do this one for the X summations and this for the Y summation. So that's kind of our basic format, except that I want to make it clear I'm not going to write all this every time. So the summation that I'm going to use, and I just want you to see this when you see what I'm actually going to write, I'm just going to do this. Okay, so this would just be the sigma for the x increments, the x summations, and that would be equivalent to this, and then the same thing, the y summation would pertain to this. And so I'm just going to write this later on when we actually get into the proof. I teach college math, and I find sometimes it's easier to give a concrete example before giving something general. And so I just made up an example here. So you know, these could be numbers in a hat or a spinner or whatever, but here I just made up the values for x of 1, 2, and 3, the only values they can take on, and for y, 4 and 5. I deliberately didn't do the same number of values because nothing about this proof depends on having the same set size for x and y. And so, you know, you could think of this as xi, but I'm not going to write those in there. You could also think of these as, you know, j, y, yj, just a particular value for y. And so if you wanted the expectation of the random variable x, well, I'm just gonna do the arithmetic. This is just all arithmetic, and I want to demonstrate that the sum of the expectations is the same as the expectation of the sum. So if we did the expectation of x, we would do 1 times the expectation of getting 1. Then we would do 2 times the expectation of doing 2, and I made sure the probabilities were different just to illustrate. And the probability of getting a 3 is 1/2. And if you sum this up, you get 2.3. Same thing with y. We would just take each occurrence. So 4 times the probability of getting 4 plus 5 times the probability of getting 5. And when you do that, you get 4.6. And if we did the expectation of the sum, so you have a hat with 1, 2, and 3 in it, another hat with 4 and 5 in it, and you keep, you know, if you did every possible combination of reaching into both hats, picking the two numbers and summing them up, and then what's the expected value of that, basically the weighted average from that. Well, that would come from just doing a summation of every possible combination of 1, 2, and 3, and 4 and 5, and times their probabilities. So if we think, okay, we got 1 and 4, so we add those up, and then what's the probability of getting 1 and 4? Well, it's, okay, so here's what I'm going to do. Let's think about probabilities for a second. The probability of getting 1, well, actually, okay, the probability of getting 1 and 4 would equal the probability, and I'm not going to go into, you know, the whys of probabilities. Hopefully this is something that you know basically how probabilities work. Well, you would take the probability of getting a 1 times the probability of getting, well, actually, okay, the probability of getting 1 times the probability of, I'm thinking ahead of what I'm going to write rather than what I'm writing. Okay, you can split them up. The probability of drawing a 1 and then a 4 is the same as the probability of getting a 1 times the probability of getting a 4. And that would just be, in this case, it would be 0.2 times 0.4. Before I go on, I want to point out that whenever you have all the probabilities summed up of anything, it's going to sum to 1. This sums to 1, this sums to 1. And another thing I want to point out is even if x and y are not independent, even if they are dependent and you have conditional probability, it doesn't change the fact that the x probabilities, even if they depend on y in some way, they still have to sum to 1. And same thing with y. Everything that could happen with y the probabilities summed up, even if y is dependent on x, they're still going to sum to 1. And so the cool thing about this proof is we're going to depend on these probabilities and these probabilities always summing to 1, whether they are conditional or not. And so the property that the expectation of the sum is the sum of the expectations, that does not depend on whether the random variables are dependent or independent. And that's a really cool thing about this. It's just nice to know that we don't care about independence or dependence when it comes to the property that the sum of the expectations equals the expectation of the sums. To clarify a little further, so the probability of x, a particular x and a particular y, it doesn't matter if they're independent. You have the probability of x times the probability of y, or the probability of x times the probability of y given that x. That we will have the same result in this proof whether we have this scenario or this scenario. So continuing on here, so if we drew 1 and 4 and we sum them, we're basically going to get, let me go back to red here. Now let's see, 0.4. Okay, so the probability of getting a 1 and a 4 would be 0.2 times 0.4, and we multiply that by the occurrence. And we continue on here. Then the probability of getting a 1 and a 5. So I'm just keeping x constant at 1 and doing every iteration of y, and then we'll change x to 2 and we'll do all the y's, and we'll change x to 3 and we'll do all the y's. So 1 plus 5, well, that would be 0.2 times 0.6 for the probability. Okay, and then moving on down here, now we increment x to 2, and we're going to do 2 and 4. So now we're doing this and this, then we're going to do this and this. I'm making a big deal out of that because I want you to get that order in your mind in case the summations you're maybe not super familiar with them, especially a double a summation, and I want it to make sense to you. And then what's the probability of getting a 2 and a 4? Well, it's the probability of getting 2 times the probability of getting a y of 4. And then x is still at 2, but we need to do the other y, and that would be the probability of getting that x times the probability of getting that y. And now x is going to be 3. And then we could have a y of 4, or we could have a y of 5. And the probability of an x of 3 is 0.5. The probability of a y of 4 is 0.4. And then 0.5. The probability of a y of 5 is this. And if you do all the arithmetic here, you get 6.9. And if you sum these two up, you also get 6.9. And so that's just one example of infinite possibilities, just demonstrating that the expectation of x plus the expectation of y equals the expectation of the sum of random variables. And so now that we've had a live example, let's go ahead and do a general format. I should have had a plus there. By the way, this here, just think of this as this. That I'm just kind of shortcutting stuff here. So the probability of random variable big X being this particular value, it's just the same thing as the probability of that value. Okay, now to do the actual proof, we're gonna start from this, and we've seen that by definition, if we use a double sigma, double notation signs, and then we do that to increment the x's, we do that to increment the y's, and then we're summing all the occurrences of x and y, and then we multiply that times the probability of x times the probability of y. So I've written them together here, but later we'll split them up into the probability of x and y is just, you know, like we've seen, is just that, but we'll do that later. Okay, now hopefully you're somewhat familiar with sigma properties, with the sigma notation. When you have okay, just as a real fast example here, I'll just take this. This is the same thing as distributing. It's not multiplicative distribution, but it's still a type of distribution. You can actually sum the x's and the y's up separately. That's just a basic property of summation sigmas. And so what we're going to do is distribute this double sigma into one into x and one into y. And of course this is multiplication, so one of these is going to have to be with the x and one's going to have to be with the y. And so when we get that, actually I may not have enough room, so let's just come down here. So we're going to do one set for x, and then that probability is distributed in by multiplication, and then we're going to do another one for y. Yeah, why do I keep doing that? Okay, and so that gives us this, and then I'm actually going to switch the x and the y sigmas because the order doesn't matter. So just again to emphasize how double sigmas work, what you would do is say x is stuck on I equals 1. So you know, it's xi. I'm just not writing that in there, but it's stuck there, and you do a complete iteration of y's. When you're done with that, then x would go to x2, and you would do another iteration of y's, and then x would be 3, and so on. And so that pattern needs to be clear in your head, how that works, to make sure that this all makes sense. Okay, and then you know, it doesn't have to be done in that order. We could have done all the x, we could have left y stuck there and then done this and all of this, and same thing, the order is not going to matter when you sum, so we can put xy or yx. Another thing we can do is let's move this x in front of the y sigma, because the y sigma is not going to increment the x's, and so we can change that order. And same thing here, I'm gonna put the y out in front because it is not incremented by the x sigma. Now let's hold up and look at what's going to make this proof work for us. We want to just look at these guys. Okay, so this is where x is just sitting here. We're going through all the iterations of y, and it's really, in this case, it's the iterations of only the probabilities. And here's what I want to prove to you. Let's just take this one. It doesn't matter which one. And let me line this off. And let's just take this thing, and let's go through it. Now you can picture, if you want, you can picture the x sigma out here waiting for us to go through this iteration of y's, but just picture it there. I'm not going to put it there or leave it there, and let's just think what is actually going on here. And so these are actually here, when I do probability of x and y, I'm going to write them separately. We've already seen that that's correct. And actually, so that I don't run out of room, I think I'm going to write it down here. Okay, so now keep in mind x is sitting there constant. It's just, in fact, let's put a little c there. And then y, you could think of a little j that's going to keep changing, but the x, I'm not going to put the j, but just think of it. Y is changing according to this, x is sitting there constant. And so we're going to end up with the probability of that particular x times the probability of y1. Then we're going to do it again. Probability of that x times the probability of y2. All the way till we get to the last y that is possible. And so we get to the probability of that constant x times the probability of yn. And now we can factor that constant x out. In fact, I'm just going to leave the c off now. It's just some x that is sitting there constant. It is not being incremented. And now we have probability of y1 plus the probability of y2 plus probability of yn. So this is the summation of all the probabilities of y, and we already know that equals 1. So this is the probability of x times 1, which is just the probability of x. And so what I want you to see here is the probability, and I'm going to take that c off because the point has been made now. And I just want you to see that when you have a y summation of a probability of x and y, and x is held constant, ultimately it just equals the probability of x. The summation just equals nothing more than the probability of that x that is sitting there and has not incremented yet. And so this identity is what we're going to use. This is, if you want to look it up, it's called the marginal probability mass density function. But whether or not you investigate that further, we can go ahead and complete our proof. So here, okay, this thing here, just turns into the probability of x. And this thing here, in the same way, turns into the probability of y. And we're done. Because this is the definition of the expectation of x. And this is the definition of the expectation of y. And we're done. We've shown that the expectation of the sum equals the sum of the expectations. Quick little corollary to finish with. So if you have the expectation of a random variable with a constant in front of it, that's equal to the constant times the expectation. And so if you think about it, a times x is just x plus x a times. And then we've already seen that the expectation of a sum is the sum of the expectations, so we can get from this to this, and it happens a times, and so you simply have a times the expectation of the sum. And so basically this is an important identity here. It's very useful to be able to factor out a constant from in front of a random variable. And then by extension, so if we took what we did before, except we have constants in front of x and y that are not necessarily 1, well, expectations, we've seen that expectations are just sums, and in the same way a sum can be distributed in front of each thing that is separated by plus or minus. Well, we can do that. We can get from here to here, and once we get to here we can factor out those constants in front, and so we get from here to here, which is another good thing to know. Actually, I might mention while I'm here too, the expectation of a number is just the number. I'm not even going to prove that. It's so intuitive, you know, I'm not going to bother here. But the expectation of 3 is just 3. The expectation of a constant is just the constant. And so if you're in statistics, you'll see that property pop up as well.